Hi, my name is Teresa O'Donnell Sloan and I'm a senior at Pomona High School in Arvada, Colorado, and today we'll be talking about integrals. There are two types of integrals. The first one is an indefinite integral. This integral allows us to find the antiderivative of the function in which the integral is being placed upon. The second one, what I'll talk about today, is the definite integral, and this integral allows us to find the area underneath the curve which has been created by the function f of x over the interval a to b. Without calculus, we would use estimation techniques like using rectangles. We would divide off this shaded region with as many rectangles as we possibly could with varying height and equal width. Then we would add all of their areas together to find the overall estimated area of the shaded region. But if we wanted the 100% accurate and exact area underneath the curve, we would use this, a definite integral. This is the notation for a definite integral, and it is integral a to b f of x, which is associated with height and is also the function, times dx, which is width. And the f of x part, or the function part, is the only part that is altered, since the height is ever changing, like we talked about here, and the width will stay the same, so dx is not altered. Also, it is 100% accurate because integrals use an infinite amount of rectangles, so since as our number of rectangles used increases, our accuracy increases, and therefore, since we have an infinite amount, our accuracy is 100%. Now we're going to solve. So how to solve a definite integral? First, we break up the integral by using these two rules. The first rule is that constants and variables are allowed to break up. The second rule is that addition and subtraction allow each component of the function to break up into its own separate integral, right, seen as here. The second step is solving through an indefinite integral. An indefinite integral is without the interval a to b, and it allows us to find the antiderivative. So first we're going to take this rule applies to all, so it's the integral of x to the n dx turns into x to the n plus 1 over n plus 1 plus c. Plus c refers to the constant which we don't know, because when you take the derivative of a constant, it is 0, so if we're taking the antiderivative, we don't know what that previous constant was. And now, since we're doing a definite integral, we have this third step, which is using the fundamental theorem of calculus, which states if f of x is continuous over the interval a to b, then the integral of a to b f of x dx equals f of b minus f of a, where f, capital F, equals the antiderivative. So we just plug in b into our antiderivative equation and get an answer, and then subtract that from f of a, which when we plug in a into our new antiderivative equation, subtract those two together, and then we have our answer, and it is our exact area underneath the curve over the interval of a to b. Thank you.